Actually, what does a 17% probability mean? So one of the questions was, question number 2, you were analyzing the hard drives, the hard disks in the RAID array here at COCC, which is where all your stuff lives, right? All your stuff lives on the RAID array, your My Documents folder, and all your data. And they always tell you that your data is safe. And I trust them. I think the data is safe for the most part on the RAID network. So what you calculated in the first part was the chance of at least one of the disks failing was 17%. What did that mean? What does that mean, 17% chance of at least one disk failure? I think this is where a lot of the points were lost, if points were lost on your project. I saw an awful lot of 23s and 22s out of 25s, which, hell yeah, nice work. But I think it was the interpretation question that probably might have buried. Trey, go ahead, give it a whirl.
It's the right answer, because I missed it. I got -1 on it, but I just put the probability that at least one fails over the next year 17%. Because that's
Which means what?
Over 100 years, 17 will fail?
Okay, so it doesn't mean that.
On average over
Average.
time.
Now, hang on. You guys hit me rapid fire. Bam, bam, bam. I love that. So first of all, what Trey said was, he said, there's a 17% chance at least one of the disks is going to fail. I said, yes, but what does that mean? Then Cody said, and make sure you see the nuance in this, he said, over 100 years, you can expect 17 disks to fail. That's getting closer. But it's not that you can expect 17 disks to fail over 100 years. Kelly?
Well, I said that over a time period of 100 years, and 17 of those years, at least one of them, yeah.
That's what you have to say. Over a time period of, say, I like this 100 years thing, you guys. I like that. You can use any long period of time, because that's what you really have to do. Over a long time period, say, of 100 years, in 17 of those years, the event you measure is going to happen on average. And the event you measured isn't that one drive failed, it's that at least one drive failed. So in 17 of those years, you may have one drive fail, you may have them all fail. You may have 5 of the 6 fail, you may have 4, but you gotta have at least one of them fail. So putting together what all 4 of you said, you get the 100% correct answer. I think that's why there were gradations of points taken off if you lost a point here or there. So you got the 100-year part, or the 1,000-year. Anybody use like 1,000 years or 10 years or a long period of time is what I was looking for. Over a long period of time. What's going to happen? What's going to happen is you're going to see in 17% of that time, so in 17 years out of 100, or in 170 years out of 1,000, or in 17,000 years out of 100,000, or something like that, you're going to witness the event that you were measuring. And the event you were measuring was at least one of the hard drives failing. Remember the corresponding question on your first project? I had you look at the incidence of, I think it was eczema and seasonal allergies in your offspring if you yourself had it. Same exact thing. When you have a percentage likelihood, you begin to see repeated occurrences of that at a percentage interval, but the interval is random. All you know is over a long period of, we saw it yesterday with the damn dice, or Thursday with the dice. I had you guys rolling one of those dice in class on Thursday, yes? You roll one of those dice over and over and over again. And I asked, what's the chance of rolling a 1? And you said it was 1 in 6, and I said, what does that mean? And you said if I roll the dice 6 times, I'm going to get a 1. And how do we feel about that? Eric said, wait, yeah, but how do we feel about that, Eric?
Well, you have a 1 in 6 chance of rolling one, but you also have a 5 in 6 chance of rolling.
Okay, for on each trial. Everybody do this right now, if you would. Everybody take one die, roll it 6 times, and keep track of what you get right now. Just right now, real quick. Roll one die 6 times, and keep track of what you get. I'm gonna make a prediction. What's up?
Nice.
Oh, you need dice and a coin too. There should be a coin bin. Here we go. Grab 1 coin, 2 dice. Thanks, sir. I'm gonna replicate your experiment too by rolling 6 dice simultaneously. God, good. We got them all. 6, 4, 1, 1, 6, 1. Okay. You need 2 grenades, Miguel. I got 3 1s, a 4, and 2 6s. Anybody get 1 of each?
One off.
1 off, almost. 1 off. Lots of 1-offs. Do you remember the chance?
I didn't look.
you remember the chance, we calculated it last week real quickly, of getting, if you roll exactly 6 dice, getting one of each? Remember what it was, 1 in?
6.
It was way lower than
It was,
that.
sorry, it was,
It was, you either, it's okay if you, 1 in 120. 1 in 120 is the calculation. You'll know how to do that calculation after the next project. I'm sorry, Jared, you were looking it up for me. So we got about 30 people in the room today. So what does 1 in 120 mean? On average, over time, we should have to repeat that experiment how many times? 120 times until we see one incidence of each one coming up. Do it again, do it again. There's 30 of us in the room. We shouldn't have to do it that long. It's like playing lotto. Count it to 4. Exactly. I got 2 3s, 2 4s, 2 6s. Anybody get one of each? 1 off. Hey, begin. Notice how we're getting an awful lot of those 1-offs. Do you know what the chance of being 1 off is?
it's a 3.
Being 1 off? It's a little tricky to calculate. It's exponentially better. It's basically about 1 in 30, 1 in 20 or something like that, which makes perfect sense. We're seeing it so much. Again, you'll learn how to calculate that in your next project. Do it again! If you remember correctly, the Excel spreadsheet was 1 off last week. If you remember when we did that class. 1 off for me.
I wish I was playing that.
1, 2, 1, 2, 3, 4, 4, 6 for me. I'm 1 off as well. Anybody get them all? Get lots of closes. Well, while you're doing that, actually.
Does it matter how much you shake it today?
That's a good question. I don't think it does. No, is that your question? That's a really good question. The question comes up one of randomness. Randomness. So, how many of you have heard, you're holding a coin in your hands, yes? You're holding a coin in your hands. So the question that Zach just asked is, how does randomness tie into this? Well, I read a research article years ago that said, heads and tails really aren't everything. And what the article, and this is a great article, one of those articles that got my attention, I'm like, okay, prove it to me. And what this researcher did was, he built a flipper that he loaded a coin into the exact same way each time, and flipped it so that it basically it got to that perfect point of random flips the same consistently each time. And he was able to measure over the course of 30,000 or 40,000 trials that there was a slight edge on either heads or tails. And the article's headline, about not being heads or tails 50-50, got leaked onto the internet, of course, and it became partially mathematically viral. What they failed to do was read the very last paragraph of the article, which said, but when you flip a coin with your thumb, you're nowhere near as consistent as this flipper, so therefore it's basically 50-50 when you flip a coin with your thumb. So in other words, this great article about randomness, about perfectly designing randomness, is thrown out as soon as you don't use the flipper this guy built. So the question, I think, is, any randomness is probably taken care of. Somebody might be wondering, if I throw 6 dice at once, is that any different than you guys throwing 1 die 6 times? My answer is no. There's so much butterfly effect going on in both of those things that it basically can't, it's no background. Steven?
I heard the reason for that slight possibility.
Yes.
That the head side
Yes.
is heavier.
It is heavier. And if you spin a coin and let it come to rest, something surprising happens. But when you flip a coin, you grab it and stop it while it's spinning, which means it hasn't had a chance to have inertia kick in yet. We'll test that in 244 if you guys take 244 with me. It's one of my favorite experiments. Yeah, you're right about that. At least the old pennies, definitely. The new ones, maybe too. They changed, in 2006, they changed the style of penny. But the old pennies, definitely. Let me fire a spreadsheet up real quick. Anybody get one of each? Roll one more time. 2 dice, maybe. Yes. 3, 3, 4, 5, 2, 2. I was actually out here a whoop that happened. Whoop! That was not much of a whoop. That was very understated, gentlemen. We got it! We were expecting 1 at about 120, and we got, I wasn't actually expecting it at all, just because it's an average, but there it is, we got 1 of each. So, what did we just prove? That's pretty freaking awesome, actually. I wasn't expecting it. But we just showed that a 1 in 6 chance does not mean roll it 6 times, you'll get 1 of each. It means over time, you'll get 6. Now, what's also fun about that is, remember that first time that I got 3 1s in my 6? I guarantee in some other trials, some people got 0 1s in their 6, yes? We can then average all of that out. It'll average out to 1 per every 6. If we made a distribution of your guys' results, it would be this beautiful bell curve, hovered around exactly the average. Because the people that, did anybody roll like more than 3 1s in any one of their groups of 6? Did that ever happen? We got that Cheyenne, you got like 4, maybe 4 1s? 4 1s in a group of 6, right? And I got 3 1s in a group. These are high numbers, you shouldn't see that many. But then I bet you some of us got no 1s at all sometimes, yes? And what that is it averages out to 1 per every 6. But as humans, we forget that bit about the average, the long run, the long term. Which is why I'm always harping on it in this class. Fair enough? Good, good. Thank you, friends. Thank you for the experience. Super fun. Thank you, Tyler. Very nice, very nice.